Kim, Professor, School of Mechanical Engineering, Yonsei University, Korea, on the topic Characteristics and Prevention Microscale Wear Phenomena. I invite Dr. Dae-Eun Kim onto the dais. And I request Dr. R. Manu, Associate Professor, Department of Mechanical Engineering, NIT Calicut, to chair the plenary session 1 and introduce the keynote speaker for this session.
Good morning to all. This conference, ICAT14, is starting with the plenary session by Professor Dae-Eun Kim. Professor Kim works in the area of biorobotics, artificial intelligence, neuroethology, neurobiology, and artificial life. I'll give a brief biodata of Professor Kim. He had his BS in computer engineering from Seoul National University. I will request Professor Kim to take over.
Okay, thank you very much. I don't know if you can hear me. Thank you for the kind introduction. And I would like to thank the organizer for giving me this opportunity to come and speak to all of you in this plenary session. As you can see, the title of my presentation is Characteristics and Prevention of Microscale Wear Phenomena. And I think today our chief guest had expressed a lot of concerns about tribology and its impact in technology. And it's a very good introduction for this conference, I think also for my plenary talk. Thank you. I'd like to first start out with a little introduction about my university. It is situated in the capital of Korea, which is Seoul. And our university has about 22,000 undergraduate students and about 7,000 graduate students. And before I attended this conference, I was attending the Asia Trip Conference at Agra. When I left Korea a week ago, the lowest temperature was -2 degrees Celsius. And when I went to Agra, it was about 7 to 20. And now here in Calicut, it's about 20 to 32. So over the past 1 week, I went from winter, spring to summer. And certainly in the summer, it's most delightful. I'm very glad to be here. This is the picture of our campus during the autumn. And these are all buildings, and the lights are lit throughout the night with researchers producing a lot of good work over the years. Well, with that very brief introduction about my university, I would like to ask all of you a very grand question, which are actually our chief guest also mentioned. And that is to ask what we think is the greatest invention of mankind. I'm sorry, you cannot see that up there. Can anybody tell me what the greatest invention of mankind is? Exactly. It's the wheel. And this is what our great chief guest also mentioned. It's very coincidental. But certainly, we think that this is the greatest invention of mankind. And when we think about it, what was the purpose of this invention? The purpose of this invention was to overcome friction. And what was the impact of this particular invention? The impact is beyond several Nobel Prizes. The impact of this particular invention, it simply changed civilization. Now, the ability to move one material from one place to the other I'm sorry. The ability to move from one place to the other changed many things, transportation, and had implications in various fields of technology. Also, if you look at this picture here that we often find in historical textbooks of tribology, you see this great statue being moved by a lot of people, a lot of slaves. But here is one friendly person who is allowing this task to be done very well. And that is this first tribologist in the world. And this person, I think, this person is basically lubricating the interface to make the sliding take place easier. And this image was found in the walls of Egypt maybe 4,000 years ago. After several thousand years, what do we have today? We still rely heavily on rolling elements and lubricants like bearings. Without these, machines will not survive. Also, is this the best we can do? Well, currently it seems like it's doing a good job, and it's the best we can do so far. We're getting more precise, we're getting more smaller, but we have to be cleaner because we're talking about green tribology and we're concerned about environmental problems. Well, after 5,000 years, what do we think is the next revolutionary invention? This will depend on your individual thoughts, but maybe some of you will agree that perhaps molecular machines would be the next revolutionary things. Being able to make things very, very small at scale so that we can probe into the bodies of our body without opening our skin with minimal invasive surgery, and also probing into microscopic things to do some sensing and also diagnostics and also prognosis. This is an artist's view of what a molecular machine looks like. And actually chemists are trying to make this kind of machines right now around the world. Now, the crucial role of tribology in making this kind of motors being able to run with sufficient reliability and low friction. And without tribology, this ultimate precision engineering will not be realized. So fabricating the molecular machine is one thing. Perhaps many of you have seen like MEMS motor developed like in a place like Sandia National Lab with very cute micro MEMS components that's able to spin at very high RPM. But right now we do not have a single commercialized MEMS product that depends on gross sliding motion. A lot of the MEMS products are based on elastic movements like accelerometers. Now what is the reason why, despite the fact that this kind of very fancy MEMS component was developed many, many years ago, we do not have a commercial product? The reason is because we cannot overcome the surface forces, which become so dominating, especially at micro scales. So this is an example of a micro gear composed of many elements, mechanical elements at micro scale. We start running this component because of surface forces, it fails and it's not reliable. Because these systems cannot work with conventional lubricants because the lubricants will dominate the forces due to its surface tension. So these must operate in dry or with very nanoscale lubricants. Preventing wear would be a greater challenge in this kind of systems. So with the brief introduction, what are the challenges that lie ahead? Despite the fact that tribology has been researched over decades, perhaps hundreds of years, can we control friction? The answer is no. Can we achieve zero wear? And the answer is no. What are the mechanisms? We're still trying very hard to understand why friction occurs, why wear occurs, to be able to prevent this in the ultimate end. What about macro versus micro phenomena? Tribology occurs over a very wide scale. Even earthquakes are related to tribology. Oil drilling, excavation, these are all macro scale tribology. Machining. But now you can come into this kind of micro scale tribology where you have micro components rubbing against each other. The conditions are completely different, and friction and wear is a very system-dependent phenomena, as you all know. So great challenges lies ahead. So with that overall background, these are the concepts of my talk. I know I'm giving about 1 hour for my talk, and I would like to talk about several topics that we've been doing over many years in our lab, so I will not bore you with one subject going deeply into it. First, I'll talk briefly about macroscale friction, especially the effect of particles on friction and wear, and what we can do to eliminate this kind of problem. And then I'll move on to microscale tribological characteristics. And microtribology actually started because of this technology, very important technology called hard disk drive. Hard disk drive was the ultimate driving force behind the development of microtribology as well as nanotribology. It's a very well established technology, and I would like to review some of the technology that went into the development of hard disk drive. Then I'd like to talk about the atomic force microscopy, which is the most important tool that is used in nanotribology, and the wear associated with such devices, and talk about silicon bushings, which are used in MEMS to reduce the contact area to reduce stiction, and discuss about the wear of these components. Basically, the AFM probe tip and the wear silicon bushing represents high versus low contact pressure for silicon-based materials. And I'll tell you that despite the fact the materials are similar, you have very different behavior in wear because of the level of contact pressure. Then I'd like to further go into the way we can exploit wear for lithographic process. Lithography means trying to make very fine grooves on a certain substrate. How we can utilize tribology for this kind of technology. Then if time allows, I would like to go into atomic scale surface design based on molecular dynamics simulation to be able to design surfaces that we want ultimately that can produce low wear. And end with some concluding remarks. This is the very simple model of a sliding interface. All of you know that tribology is a very complicated subject, and the reason is because the interface itself is very complicated. No single surface is perfectly smooth. We all have asperities. So when you have materials in contact, we're dealing with asperities contacting against each other, which is rough. The surface has oxide layers and also contamination layers. You have roughnesses, and when you apply a force and try to move in the tangential direction, you have to overcome friction. And this friction is due to many things, such as adhesion between the junction, such as cold welding. Sometimes if it's a humid environment, you would have capillary junctions, leading to some stiction problems. And if you have some mechanical interaction such as this, you will have abrasive action. So all these very complicated phenomena are going on at the interface, and we have to be able to control this. In describing this very complicated phenomena, we use two coefficients, as you all know. First one is the friction coefficient, and the second one is the wear coefficient. Perhaps this may not be so familiar to you. Wear coefficient is defined by the wear volume times the hardness divided by load and sliding distance, represented by Archer's wear equation. In tribology, what we're trying to do is to first be able to predict what the friction coefficient is B, which is in the range about 0.001 for a very well lubricated system, can be as high as 1 or above for dry systems. And for wear coefficients, it can be about 10 to the minus 2 to 10 to the minus 8, depending on the system. Very wide range. So what is the purpose of tribology? Trying to be able to predict these coefficients and ultimately being able to control these coefficients. Are we able to do that? And the answer is no. We're trying very hard, but we're not able to control these values accurately enough for various technologies. Now, given this kind of complicated situation, what do we know about macro-scale tribology? Firstly, as you all know, friction coefficient is not a material property. It is a system-dependent property, and it changes with history, and it changes with system. This is a data that gives you a very good example of such a characteristic of friction. What you're looking at is the friction coefficient versus sliding distance. If you have two metals sliding against each other, in this case titanium on nickel, you can see that the friction coefficient starts slow and then suddenly rises and reaches a steady state. The point of interest is, why does this friction coefficient increase? Well, if we observe the sliding interface with a microscope, with a pin, and this is a flat surface here, the thing that you see here is a reflection. So you may ignore this cone-shaped thing at the bottom. It's just a reflection of the top surface. Bottom surface is flat. At the point at which the friction coefficient starts to increase, we see the creation of a significant wear particle. And this particle serves to damage the surface by way of abrasion and micro-cutting. Obviously, the friction goes up. And once enough number of particles are created at the interface, you sort of reach a steady state as the particles ejected from the interface and also created at the interface. By knowing this, what we can do is we can reduce friction if we eliminate the wear particles. And indeed, this data shows that. This is the friction coefficient versus sliding distance or time. As you can see, the friction coefficient begins to increase again, and when the particles are removed, it goes down. And the particles are created again, and the friction coefficient goes up again. Now, in this case, the particles were removed artificially using a brush. Now, how can we do this automatically? The way to do that is by texturing the surface so that the textures are able to trap the wear particles. And these are undulated surfaces that we've been researching over a long time now. And this is an example of such a surface. What you're looking at here is a silicon surface with grooves artificially fabricated on the surface to trap the wear debris that is being created. On the top surface, you see a regular flat surface after the wear test. What you're looking at here is, in the case of the bottom surface where you have micro grooves, it is able to lower the friction by trapping the wear particles in these grooves. This is the friction coefficient versus sliding distance. And at this point, we input the particles artificially, and the friction shoots up. But because of the grooves, it is able to self-clean the interface and lower the friction. Now we input the friction, the particles again, and the friction coefficient shoots up again. And then it is able to, again, eliminate the particles and reduce the friction automatically. So we have to use this kind of texture surface as much as we can in many mechanical systems to be able to reduce the effect of plowing action by the wear debris being created at the interface. So this is a conceptual idea about what texturing is. We would artificially fabricate these grooves on the surface that can act to trap the wear particles. And also in the case of lubricated systems, these traps are able to contain lubricant as reservoirs and being able to supply them to the interface more readily. Now this kind of concept actually was proposed to cylinders and engines. And if you know about the lubrication state of engines, the piston ring travels between the top dead center and the bottom dead center. And in the middle section, it travels very quickly, and the interface between the piston ring and the cylinder liner is separated by a very thin lubricant film. In this case, the lubrication condition is hydrodynamic, and we do not expect much problem in terms of friction and wear. However, at the top dead center and the bottom dead center, the ring stops momentarily, and you have pressure of the piston ring going against the cylinder wall, and this is when you go into mixed and boundary lubrication, and this is when you expect to have more problems. So what we've suggested is to avoid the problems at these extreme conditions, to texture the surface at the top and the bottom, and to make the friction lower and be able to increase the fuel efficiency even by a fraction of a percent. Now I took this idea to car companies, and the first thing they said was, "Professor, that's a very good idea, but it's not possible because it costs too much." This idea was proposed actually 20 years ago. And surprisingly, today, at a company called Doosan Industries in Korea, is making engines like this for heavy-duty tractors. So they're using laser techniques to groove the top dead center and the bottom dead center to be able to increase the efficiency of their tractors. It's not so feasible for passenger engines right now because it costs too much. But for specialized engines like ship engines, like tractor engines, helicopter engines, this is a very feasible method to be able to reduce some of the problems we face in these engines. That's all I'm going to say about macro scale friction, because after all, in the case of macro scale friction, texturing and lubrication are efficient so far in controlling the friction and wear down to a level that we can deal with. Now, problem arises when we go into the microscale. Next topic, I'll talk about microscale tribology. As I told you earlier, hard disk drive, as you know, it goes into every computer, has a tremendous amount of tribology inside the machine. And without microtribology developments, hard disk drives will fail immediately. The thing that I'll be talking about is not about current hard disk drive, which is much more advanced than what I'll be talking about. The technology that we've been using with regard to this particular talk is quite old, but it is so precise, and in terms of scale, it's in the nanoscale. I would like to introduce to you. If you look at the hard disk drive, it's composed of a slider disk on a slider head on a magnetic disk. The magnetic disk is composed of several layers, and the disk flies over the slider flies over the disk at a very low height. The height is only about 10 nanometers. Now, there's an incentive to lower the height so that the head can be closer to the magnetic element. In this case, the recording density will increase. So the industry is trying to lower this height down and down and down furthermore. And right now in today's hard disk drive, if you buy a hard disk drive, the flying height is only 2 to 3 nanometers. It's just mind-boggling to imagine that the slider is flying at that height. Obviously, the problem faced is that because sometimes you may have contact between the slider and the disk, you will have friction and wear problems. And this is what we want to avoid. And if we look at the way the disk is structured, it is also composed of complicated textures, including what we call a landing zone. The landing zone is a textured region where you have these small protrusions on the surface, and these are made by laser texturing. The purpose of these textures is to be able to reduce the stiction between the slider and the disk when the slider lands on the disk when you turn off the computer. Without these grooves, the slider, because of its smoothness, will stick right on the disk and you will not be able to start the disk. So laser texturing is used to make such grooves, such patterns. And when you turn off the computer, the slider will go to the landing zone and park there and settle down on this track. Of course, the wear of these tracks will be very important because it is sliding against the slider as the speed lowers. And lubricant is used, PFP. Perfluoropolyether is a lubricant developed for this purpose. It's a fantastic lubricant with a thickness is only about 1.5 to 2 nanometers in thickness. So it's not like a liquid lubricant that we use in ordinary machines. It's a very semi-solid-like lubricant that's coated on the substrate, and by dipping process, so you have a solution and you dip the disc and it's automatically coated on the surface. But it's a little bit more complicated than that, because some of the molecules are attached to the substrate by way of chemisorption, in other words, by chemical reaction, so the bonding is very good. However, for most of the part of the lubricant, it is attached to the surface by physical absorption, by van der Waals forces, and these are very loose molecules that have mobility and can move around. It turns out that the percentage of these mobile molecules is important, because if the lubricants are removed from the track due to some contact, you'd have to replenish. In other words, the lubricant should be able to flow back and fill in that location. So the percentage of this physically bonded lubricant is important, but if you have too much of it, it will again pose some problem. Now, how do you control the percentage of this physically bonded lubricant? You do that by process of annealing. So by controlling the temperature and the time of annealing, you can change and adjust the percentage of the bonded part to the unbonded part. So give you a schematic of what's going on. Here's a slider, and the head is at the tip of the slider, and you have lubricant on the surface, and during interaction you have some lubricant transfer, and this can contaminate the head and make problems in terms of signal transfer between the head and the disc. And as the flying height decreases, the lubricant transfer occurs to a greater level, and as I told you before, lubricant mobility and bonding ratio is important. So what we do is, first in this experiment, we want to see the effect of annealing to see how annealing affects the flyability of the slider above the disc. And this is a simple test equipment. It's a commercialized equipment that has a slider and a disc, and the slider, this is a slider that you see here, and you cannot see the head, but head is a very small thing at the end of the slider. And we conduct this experiment in what we call a contact start-stop test. We start it, stop it, start it, stop it. We repeat this for 20,000 times. We can also do this test under drag test, in which we make the contact between the two specimens and run a sliding test at low RPM so the slider will not fly above the disc. And these are the conditions at which we perform the experiments. And we have an acoustic emission sensor to monitor any signal, abnormal signal between the head and the slider, the slider and the disc. And also we have friction sensors to monitor the frictional force. With 1.5 nanometer coating of the PFP lubricant, this is the stiction coefficient that you get over 20,000 CSS cycles. Without the lubricant, you will see that the friction is very high and the hard disk will fail immediately. That is the power of this 1.5 nanometer lubricant, which is not really a liquid. It's semi-solid, but it works tremendously well in hard disk drive, and this is what makes today's hard disk drive work. Now, this is the effect of PFP on flyability without annealing. This is the signal of acoustic emission signal, and this is the friction signal. You can see that there's quite a bit of noise in the signal. And after you do this test, we disassemble these parts, and we look at the slider face, and you can see that the slider face is contaminated with lubricant. These are all patterns on the slider that allows the slider to fly at a certain height. But you see streaks of lines which are contaminations from the lubricant on the disc. If you anneal it properly, you can see that the signal can be very well controlled to a very stable level. And again, if you look at the transfer of lubricant to the slider, you can see it is significantly less than what you see before. Therefore, by annealing the lubricant at a proper condition, you can control this problem of friction to a certain level. Therefore, in the case of a very well commercialized product like hard disk drive, surface texturing and nano lubrication for stiction and friction reduction is a very commercially viable technology. Now, what we hope is that we hope to extend this kind of technology to other microsystems, such as MEMS that I showed you earlier. But without the drive from the industry, this kind of technology will never be utilized at the industrial level and only be limited to lab scale. Now I'd like to move on to another very important topic of nano and microtribology, and that's the issue of atomic force probe wear. Atomic force microscopy is based on a very sharp tip that scans over a surface, and the deflection of this cantilever is measured using a very sensitive laser interferometry. And by noting the amount of deflection, we can map the surface. And if you scan this in X direction and Y direction, you're able to map the surface topography in 3 dimensions. And we can buy this equipment commercially, as you all know. But the issue is, because it uses a very sharp tip, there is an issue of wear of the tip as it slides over the surface of your sample. The tip material that we commercially use are silicon nitride. Sometimes we use diamond, which is much harder. The applied load is in the range of a few nanometers to can be as high as a few micronewtons. I mean, few nanonewtons to a few micronewtons. The sliding speed is the order of tens of micrometers per second. This is how we can utilize this amazing equipment to study nano-wear. What you're looking at here is an AFM experiment that was conducted on diamond-like carbon film with a surface roughness of 0.8 nanometers. First, what you do is you pre-scan the surface using 4.5 nanonewtons, and this is what the surface looks like before the wear test. Without removing the specimen from your AFM, you take a diamond tip and you scan the surface to do your wear test under 4 micronewtons, and over 1 cycle it was performed. And after you're doing the wear test, again, you change your tip to your silicon tip and you post-scan your tip to image the surface. This is the image that you get after the wear test. This is the image you get before the wear test. You can use this kind of features on the specimen as references so that you are sure that you are on the right location, which is very difficult to do actually. If you superimpose these 2 3-dimensional images and look at it in the 2-dimensional, you're able to see that the profile initially has been decreased due to wear. And this is the level of accuracy at which we perform nano-wear test. The accuracy and resolution is down to the 0.0 nanometer scale. Now obviously, the accuracy of this particular wear test will depend on the wear of the tip itself. So we've looked at the wear of how the sharp AFM tip wears. Now, if you had a feature like this on your specimen, and if you use the sharp tip, you will have this feature represented very accurately with your tip. However, if you use a blunt tip that's been worn out due to contact, this particular feature will look like that. And therefore, it is of great advantage to make sure that you use a sharp tip when you want to make good measurements using your AFM. And many times, users don't realize that you just use the same tip to measure the surface because of convenience. And these tips are expensive, so you don't want to replace them every time. But you have to be aware of the fact that tips do wear out and it will affect your measurement significantly. So what we first did was, what is the mechanism of AFM tip wear? These tips are made of silicon because of ease of manufacture using photolithography techniques. But actually, it's not silicon that is touching your specimen. Because of it's exposed to the environment, on the surface of the silicon tip, it is covered with amorphous layer of silicon oxide. And actually what you're doing is the silicon oxide is in contact with your tip of your specimen. And when you rub it against each other, it's this amorphous layer that's being worn out. And we can look at the TM image of this amorphous layer, and it's well represented. And the radius in this case of this particular tip end is about 6 nanometers. Typically, the tip radius is in the order of about 10 nanometers to about tens of nanometers. So another thing that we should be aware of is the tip damage during approach. If you have an AFM tip, you're trying to approach your specimen, but if you do it at the wrong rate, you will damage your tip in that approach process. What you're looking at here is a normal force in nanonewtons, up to 5 nanonewtons, and this is the time of loading. And you can, in this very short time of low force loading, your tip shape remains intact. In other words, you do not damage. However, if you increase the rate at which you approach the surface at this rate for a very high load of 15 nanonewtons, you can see that you've severely damaged your tip just by approaching the tip to the surface. So this is another thing that we have to be aware of when we're using the AFM. Now, we looked at the wear of the silicon tip and what the mechanism of silicon tip was, and our point was to try to be able to quantify the amount of tip wear in this AFM operation. What we did here was we performed 320 micrometers of sliding on silicon surface, and what we find is that the region at which there was contact was flattened due to wear. And by noting the shape of the tip before and after the wear test, we are able to quantify the wear amount. And also, furthermore, we're able to suggest the mechanism of wear. And this is the mechanism we suggest, is that the silicon tip becomes oxidized, and this oxidized layer, because of abrasive adhesive action against the specimen surface, will eventually wear out. So, this is another test we did, and we looked at the progression of the tip wear with respect to load. And the load we used was between 10 nanonewtons up to 50 nanonewtons. And here looking at the wear volume and the wear coefficient. And this is the sliding distance. What you can see here is that the wear coefficient initially is very high, but it decreases as the wear increases. And the reason for that is because the contact pressure decreases as the tip gets blunted. The important outcome of this particular research was in quantifying the amount of wear. The wear coefficient that I introduced to you earlier for the case of AFM tip is in the range of 10 to the minus 2 to 10 to the minus 3, which is in the category of severe wear. So even despite the fact that the loads that we use in the nanonewton range, even for AFM, which is used for nanotribology research, the kind of wear we get is in the order of 10 to the minus, the wear coefficient is about 10 to the minus 3. Now I'd like to move on to wear of silicon bushings. Now what is silicon bushing? This represents the low contact pressure as opposed to the case of the AFM probe tip, which experience very high contact pressure. Bushings are used in MEMS products to reduce the stiction by reducing the contact area. And also in the case of humid environments, because of the capillary forces that are present between the contacting surfaces, by using micro bushings, you're able to reduce the capillary area, and therefore you can reduce the stiction force. This similar design was used in the landing zone that I introduced earlier on hard disk drive disks. The problem now is that these bushings that are fabricated on MEMS components wear out themselves. And these images show you that these bushings are severely worn out with operations, and these bushings are in the size of a few to a few tens of micrometers. So in this study, what we want to do is to quantify the wear of the bushing and compare the wear with that of the AFM tips. This is the experiment we performed. Basically, we took a silicon piece and we fabricated 3 bushings on the specimen. And the specimen height was, the bushing height was about 500 nanometers. The dimension of the specimen was 3 by 3 by, not micrometers, that's millimeters. The bushing diameter was about 30 micrometers, and that's what it looks like in AFM, and that's the profile of the bushing in 2 dimensions. What we do is a very simple experiment. We create these 3 bushings on the silicon specimen and reverse the specimen on top of a counter surface, which is also a silicon. So this is the counter surface, it's silicon, and the specimens are placed in these pockets here. There are 3, and these specimens are allowed to slide against this silicon wafer as the silicon wafer rotates slowly. Now we try to rotate it at a certain speed so that the top specimen will not bounce around. Because as you know, if you use 2 flat surfaces in wear test, the biggest problem is with alignment. So in order to overcome the alignment, we don't apply external forces on the specimen. It's a natural weight that is being applied to the counter surface. And we run this bottom specimen very slowly so that we can maintain relative flat-on-flat contact. Now, the good thing about this kind of experiment is very simple, and we can run experiments for a very long time. Unlike the few millimeters that you use for the slide in AFMs, we run these experiments for kilometers. This is before the experiment. That's after 8 kilometers. You can see that the specimen is worn out a little bit. After 15 kilometers, it worn out more. And by measuring the amount of wear volume, we're able to quantify the wear coefficient, and the wear coefficient in the range of 10 to the minus 7, which is about 4 or 5 orders magnitude smaller than that of the AFM tip. Now, if you look at the wear of the silicon oxide bushing, we fabricated silicon oxide bushings and we observed the wear. After 67 kilometers, the initially very well-plateaued bushing became like that. And from here, we can also quantify wear, and the wear coefficient was about 7 times higher, also in the 10 to the minus 7 range, but the coefficient is about 7.6. So silicon oxide, which is softer than silicon, here obviously showed much greater wear. What if we move on to a much harder silicon nitride bushing? Silicon nitride bushing, you can see that wore out very little, and the wear coefficient in this case was in the range of 10 to the minus 8, which was much lower than that of the silicon bushing itself. So what is all this showing us? It's showing us that even for the same kind of material, silicon, depending on the contact pressures, you can have tremendous difference in the wear coefficient. In the case of the silicon AFM tip, which is a radius of 20 nanometers, the normal load, despite the fact that it's only in the tens of nanonewtons, the contact pressure is in the gigapascal range, or hundreds of megapascal. In the case of bushings, despite the fact that the load was as high as 33 micronewtons, the pressure was only in the few hundred kilopascal range, and you can see that the wear coefficient is much, much smaller. So basically, this study is showing you is that, again, tribology is very system dependent. It's not a material property. Depending on the contact condition and also on the contact pressure, you can have tremendous difference in the tribological characteristics. There's 4 to 5 orders of magnitude difference, and AFM wear certainly is not at the nano level. It's tremendous if you quantify it. Now, to go into somewhere between the atomic force microscopy and bushing, what we did was to create what we call is one of the smallest pin-on-disc type of experiment. Here what you're looking at is a gold wire wear test. Diameter of the gold wire was about 60 micrometers. I don't know if you can see this, but that's the gold wire. It is contacted against a silicon wafer at an angle. And this gold wire was very carefully prepared so that it's relatively straight and the edge is flat. So the wire is in the form of a cylinder, and basically what you're doing is you're contacting the edge against the silicon wafer. And we're rotating the silicon wafer to create a wear on the tip of the gold wire. This is the amount of wear you get after 29, 58, and 80 kilometers of sliding. And the amount of wear we can quantify is by noting the volume that's been taken out from this tip of the gold wire. And when we quantify this, what we find is that the wear coefficient varies with sliding distance. It does not increase continuously. It increases and starts to go down. Now, from this, what we do is that we measure the incremental wear coefficient, the wear coefficient between sliding distances. The incremental wear coefficient is defined by this particular equation. So between sliding distances, if we measure the incremental wear coefficient, it goes up and it goes down to a very low level. And with extended sliding, basically what we're saying is that we can eliminate wear to a great extent. As the material runs in against each other and optimizes the sliding interface, you can see that the wear decreases tremendously. And we can use this concept actually to design the surface to start with. In other words, with optimized sliding, with optimized surface finishing, we can control the local contact pressures to achieve extremely low wear. And if we can do this with machines that we're using for automobile component parts and all that, I think we can reduce the initial phase at which we initially have high wear. Now I'd like to look into the way of reducing friction using micro ball bearings. As we all know, we use bearings extensively in all machines. So in the case of micro components, why not try to use micro ball bearings as well? So what we did was we tried to apply a sub-micrometer size micro ball bearings, and what we do is we place it between two flat surfaces and we drive the top surface and see the rolling friction with this micro ball bearing between the two flat surfaces. And this would be the schematic of the equipment. This is the top surface, this is bottom surface, and these are micro ball bearings placed between the two flat surfaces. And we drive the bottom stage to measure the friction force, and we monitor that by the load sensor that is attached over here. The size of the ball that we use is in diameters in the order of about 50 micrometers. That's the normal load that we use for the experiment. Now, without the balls, between silicon and silicon wafer, obviously the friction would be high and very unstable. So you have a very large standard deviation in the frictional force, and the friction coefficient is about 10 to the minus 0.2 to about 0.4. With ball bearings at the interface, they're effective in reducing the coefficient down to about 0.007 range. In other words, these micro ball bearings do work. Now, we also studied the effect of number of ball bearings. This would be without ball bearings, the red one, the orange one. With one ball at the interface, you can see that the friction coefficient can be reduced, but it's still high at about 0.2. With two balls, it goes down significantly. With three balls, it goes down further. With 50, about 30 balls at the interface, you don't have too much decrease. So the number of balls actually is not a critical factor as long as you have 3 or more, because you would need 3 contacting points to support 2 plates. So we find that by using a few microballs, you're able to lower the friction. But the problem is if you have few balls, the amount of force that's being applied to these balls would be high, and therefore you would have high failure rate. So what we did in the next experiment was to create grooves that looks like this. In other words, we created 3 grooves, 3 tracks on our silicon surface, and the groove dimension was about, you can see here is about 50 micrometers, and that's about 100 micrometers. And we place our ball inside the grooves, as you see in this SEM image, and also in this optical image. So we have 3 balls inside these grooves, and we put the top surface like this, and we perform our sliding. We use 2 types of balls, and that's a steel ball and it's a glass ball. And that's the friction coefficient of the steel ball, and that's the friction coefficient when we use the glass ball. As you can see, the initially spherical steel ball underwent severe plastic deformation. Now the problem with these micro ball bearings is, unlike macro scale ball bearings, we're unable to heat treat them. So they're in a very soft form, and you can see that because of the softness, they undergo severe plastic deformation, and because of that, the friction coefficient is relatively high. In the case of the glass ball, it is higher, the hardness is higher than the steel ball that we used, and in this case, we're able to maintain low friction coefficient to about 100 cycles. Of course, we're interested in much higher number of cycles, and this is a test that we did for about 2,000 cycles without lubricant and with lubricant. The lubricant that I call here is a nano-lubricant because it's not a liquid type of lubricant. It's the kind of lubricant that we use for hard disk drive. It's a one monolayer of organic film. So it's like a semi-solid type of lubricant. That's purpose is to reduce the stiction between the 2 surfaces. Without the lubricant, you can see that the balls fail at about 1,000 cycles. But with the lubricant, nano-lubricant, you can see that for repeated 3 experiments, we can maintain the friction coefficient relatively low up to a much large number of cycles. Now obviously, we need further optimization to make this particular technology commercially viable, but nevertheless, we've shown the feasibility of using microballs for very small mechanical systems. So, micro-rolling bearings together with nano-lubrication is promising for micro-scale applications, would be my message to you. Now I'll go into the next topic of exploiting wear for lithography process. Now the reason why I got into lithography from tribology is because, after all, if you look at the wear, it's the process of removing materials, and that's exactly what we want to do in manufacturing when we do cutting or grinding or polishing. But wear occurs at such small scale that if we can control the wear, we can control the manufacturing process and make it turn into a very precise, ultra-precision manufacturing machine process. So the concept was to apply this kind of wear process for lithography, and many people have done that, and it's sometimes called direct scanning probe lithography. Basically, you take a very sharp AFM tip and you scribe against the surface to create very fine patterns on your surface. Now, the problem with this process is because of the wear I showed you earlier, when you create these small patterns on the surface, you experience a very large amount of tool wear because of high pressure, and also you have creation of burrs at the surface, just like you would create burrs in typical mechanical machining or grinding process. And also, the amount of depth of cut you can achieve is very shallow because of the limited force that you can apply to the tip, otherwise the tip will break. So what we try to do is to improve upon this direct lithography technique and try to be able to make these groups without facing these problems. And this was the idea. It's called Mechanochemical Scanning Probe Lithography, MCSPL. Now the concept is as follows. We use the same AFM, but we do not use the AFM to machine the substrate directly because the tool will wear out. On the substrate, we coat the substrate with a very soft material, in this case a self-assembled monolayer. It's an organic film. We use an AFM tip and we program the AFM tip to remove the self-assembled monolayer at locations where we want the pattern to occur. So after mechanically removing the soft self-assembled monolayer with an AFM tip, we follow it with a second process of chemical etching. The first layer that we put the self-assembled monolayer will serve as the protecting resist in the etching process. So the exposed region will be etched and the covered region will not be etched. So after the chemical etching, we're able to create these very fine grooves. The self-assembled monolayer is a very interesting material, and it's been heavily investigated by chemists. It's a functionalized molecule with a long chain of carbon, and at one end it forms a chemical bonding with the substrate, and the substrate bonding against the lubricant layer is very stable. At the end, you can have a terminal group and you can functionalize this particular molecule to make it hydrophobic or hydrophilic or however you want it. You can also adjust the length of this chain by using different kind of chemicals. In the end, when you coat this kind of chemical on your silicon wafer, simply by dip coating, you're able to align these molecules very well on the silicon surface. And it's called self-unstable monolayer because it automatically aligns to a very stable and minimum energy state, which is represented by the schematic here. So, using this particular resist, what we want to do is to remove just the 2 nanometers of resist from the silicon surface. If we have too low contact pressure, you will not be able to penetrate the organic film. If you have too high contact pressure, when you go beyond the organic film and you start destroying the substrate, which is not what you want to do. Basically, you want to optimize the contact pressure so that you are able to just remove the silicon, self-assembled monolayer as shown in this particular figure. Obviously, this needs a lot of optimization, modeling, and also trial and error. And in the end, we're able to achieve this, and we're able to remove just this self-assembled monolayer to remove the top layer. And these are the patterns that we're able to achieve with this technology. This is a silicon surface with 1 micrometer spacing, width about 250 nanometers, depth about 100 nanometers. Obviously, you can make this kind of patterns using photolithography, but photolithography will require several steps, and you have to make a mask. And once you make a mask, you cannot change the pattern. But if you use this process, you can simply program your AFM tip to whatever pattern you like, so you're very flexible in terms of the kind of patterns that you can make. So we propose this method as a flexible way of making small number of parts with surface patterns. Not only you can do that at 250 nanometers, but if you control the process very well, we're able to reach down to about 70 nanometer grooves on silicon surfaces. And not only on silicon surface, we're able to do that on metal films as well. We're able to make these fine patterns on copper with a pattern width about 350 nanometers, a depth of about 100 nanometers. We're also able to do this in a relatively large area, over 90 by 90 micrometer scanning, and on silicon. We're able to do this on copper as well. And we can also make pockets on a copper surface, which has been coated on silicon. This would be the kind of pattern you get after mechanical scribing with 3 nanonewtons force, and this would be 2 nanonewtons force. So after mechanical scribing, you do not see the pattern. So after mechanical scribing, if you etch the surface, you will now expose the surface to create this kind of a pocket, which is about 200 nanometers in depth. You can also create this kind of micro patterns with trenches simply by programming your AFM tip to remove the resist material wherever you want. You create gratings on copper surfaces. You can also use a tapping mode to create these letters in English, Chinese, or Korean by simply programming the motion of a KFM tip. It's a very flexible way of patterning your surface. Furthermore, what we're able to do is we're able to make patterns on non-flat surfaces. When you're using photolithography technique using optics, one of the fundamental requirements is to have a very flat and smooth surface. If you don't have a flat surface, you will have problems in terms of patterning. You will lead to failures. However, because we're using an FM tip with a feedback control which is able to follow the contour of the surface, we can make these patterns even on inclined surfaces, as you see here. This is a round pocket with about 250 micrometers with a depth about 50 nanometers. And I don't think you can see this, but these are several pockets here. And we fabricated the lines at the edge of the pocket in this case, and inside the pocket. And you can see that even with inclination, we're able to make the very fine patterns on our copper-coated surface. So, the problem here is that we would like to make the pattern as small as possible, but as you can see, the pattern width of about 70 nanometers, the smallest we've been able to make was about 30 nanometers. But the tip size that we use to make these patterns is about 10 nanometers. So why are we getting such big width despite the fact that we're using a very sharp tip? This is because we're not able to optimize the etching process, and we face the problem of pattern broadening during etching. This is the SAM resist, and this is the part where we removed by mechanical action. And when we etch the surface, the etchant will penetrate below the resist area and can lead to some failures in the resist area, ultimately creating a width that is larger than the initially scribed mechanical region. So we need further optimization in this regard to make sure that the width would be equivalent to the tip size that we use. In order to see the effect of the tip size, we perform molecular dynamic simulation where we we scribe the surface using a very sharp tip, and we can look at the width of this pattern, and this will be sort of the theoretical limit of this particular process. And what we look at here is that actually the width is wider than the tip because of the van der Waals force between the molecules. As this molecules are moved mechanically, it pulls the surrounding molecules by van der Waals force. So the tip width inevitably has to be slightly larger than the width of the pattern has to be inevitably slightly larger than the tip width itself. What we further did was to see the effect of tip's geometry on the kind of width pattern we got. This is a sharp tip, and these tips represent a more realistic tip geometry. This is the TM image of a silicon tip, so this was modeled to represent a real tip better than this particular tip. And in the end, what we see that during simulation, we're able to achieve width in the order of about 2 to 3 nanometers. Practically, we're not able to achieve this, but theoretically speaking, this process, in the end, we hope was able to create patterns at the few nanometer level. So, even for this kind of lithography technique, nanotribological interactions can be utilized, and it's very important because to optimize this process, what we had to go through was we have to control the frictional interaction between the tip and the surface, and also to come up with the right amount of force to penetrate the film. Now I'd like to go into the final topic of my presentation, which is atomic scale surface design using anti-simulation. Ultimately, what we want to do is we would like to design surface. The mechanical engineers will design bulks. But I tell my students, now the age of designing bulk for different parts is moving on. We have tremendous amount of computing power. We can use computer-aided engineering. We have tremendous software, all sorts of FEM simulation we can do to create bulk shapes. But do we ever create design surface? Despite the importance of surface, we do not use this concept in our design. So ultimately, in the end, what we like to do is to be able to design the surface at the atomic scale. And because this is not practical by experiment, we perform this using anti-simulation. What is the purpose of surface nanostructure? We use coatings heavily in components, but coatings are limited because it is a dense structure, and you're limited by the mechanical property you can derive from a continuous film. What we hope to do is to be able to structure the surface. And by structuring the surface, what we hope to do is to derive elastic properties and toughness properties that we can not get with a continuous coated surface. And we can structure the surface because there is a tremendous spectrum of surface fabrication techniques that my colleagues and your colleagues are doing. They make all sorts of fancy patterns of the surface, but they do not know where to use it. They just make these patterns for the sake of making them at the nanoscale. So what we can do is utilize these structures for tribological purpose. And as I said, the purpose of using structured surface is to create surface properties not possible by coatings. And the concept here is to control surface stiffness rather than hardness. So we would like to change the paradigm from making the surface hard as possible to controlling the stiffness to optimize the pressure at the interface to reduce friction and wear. So ultimately what we hope to do is to, by achieving large elastic strain, we hope to dissipate the frictional energy that would otherwise be used to permanently deform the surface to create wear. So how do we make the surface so that it can absorb energy through large elastic strain, thereby dissipating the energy properly and not utilizing that energy to destroy the surface? We propose this kind of a surface. Basically, it's a corrugated surface. And if I were to force to make this type of surface in relation to a realistic situation, this would represent what we call a folded graphene, a layer of carbon that's been folded that chemists work with. And what you're looking at here is a corrugated surface with different geometry. And on top of that, you have another coating layer, and I put an asperity there. And there's a tip. What we're going to look at is what will happen when the tip approaches the surface, contacts against this, and slide against the asperity, how much wear will occur on the tip. This is what we want to see. Now, why is this asperity there? The asperity is there because in real situations, you will never have a perfect surface without an asperity. Asperity is always there, and we have to overcome interaction against the asperities to control friction and wear. So we tried that with different size corrugation and also with a single layer and also a bilayer. So we use bilayer and single layer surfaces as well and compare that with these structured surfaces. What you're looking at here now is contacting of the tip against the bilayer surface against the corrugated surface. And I'm sorry, that's sort of disappeared. But what we're looking at is the stiffness of the bilayer is much stiffer as expected than the corrugated surface. And we measure the stiffness by performing the simulation for all our designs, and we're able to quantify the stiffness for different designs. And when we slide over the asperity, what you're looking at here is the asperity that I showed before. It's the tip in contact with the surface, and now it's sliding in the tangential direction. You can see that in the case of the corrugated surface, it is able to accommodate the deformation caused by this presence of this asperity largely by elastic strain and thereby absorbing the energy. So the surface structure allows large elastic strain, and the elastic deformation absorbs the stress which would otherwise be used to destroy the surface. And we compare the top surface in terms of the wear, and we count the number of atoms that's been removed from the inertial position, which we quantify as wear, compared to the bilayer, where you see a lot of displaced atoms at the top surface. You see a relatively less number of displaced atoms. And we're using this kind of result as an indication that the structured surface performs better in terms of reducing the wear. So, surface structure designs at the atomic scale may open new ways to achieve ultra-low wear is the final message that I have for you. And with this, I would like to conclude my talk with further challenges in tribology. Basically, what we want to do in tribology is to be able to functionalize surface for the purpose of reducing friction, stiction, and wear. And there's tremendous things that we can do to the surface in terms of texturing, adhesion control, ultra-thin layers of coatings, and so many other things that we can do to the surface. And there are so many technology that's involved with this in terms of texturing, coating, and structuring. And what we have to realize is that there's tremendous value that we can add to the surface. And I think tribologists should try now to add value to the surface, not just to the bulk material. And if we add value to the surface, we can certainly achieve the things that we cannot achieve today. And hopefully tomorrow we'll be able to realize the molecular level machine that I showed you earlier. And with that, I would like to conclude my talk. And thank you for your attention.
Thank you, Professor Kim. Now the floor is open for discussion. If you have any questions, please.
Yeah, there have been some experiments where vapor bits are being slide, and they have observed less than one atom being removed per kilometer of plane. What is your view on that? You have done similar experiments.
Okay, the question is, there's been experiments where you have an AFM tip and you do a lot of lighting and you have one atom being removed on the AFM tip for per kilometer. Now, that is questionable. And the problem with these tribological research, especially nanotribology, is that it should be repeatable in another lab. And I'm wondering if anybody else has reproduced that factor. So if you look at my experiment where we use a bushing for up to 150 kilometers or 200 kilometers, the height of removal is about 0.00001 nanometer per cycle. In other words, when it's sliding, rotating against the counter surface, it means that there are cycles at which there is no wear, probabilistically. So if I use that analogy, I can also claim that for 1 kilometer, I only get a fraction of an atom wear. You see what I mean? So it really depends on the viewpoint that you have and whether how you approach that kind of problem. In terms of height, we can claim that.
If there are no more questions, we will wind up the session.
In one of the experiments, you are used with gold for rubbing.
Yes.
Is there any specific reason for that?
Okay, the question is, I used gold to perform sliding, and the question is whether there's been special reason for that. Actually, the reason we used that was because it was easily available to us. That's the gold wire that's used for bonding chips in semiconductor manufacturing. So we can purchase these very pure, nice, well-rounded material in rolls. But the problem was trying to make them straight into that length. Our graduate student went through a lot of trouble trying to cut them to make the edge straight. And those gold wires were cut by blade to make them flat. Another incentive of using gold wire is because they are used heavily for electric conduction also as slip rings. In slip rings, you want to have good conduction. So gold material is used for electric connectors, and sometimes you have a lot of sliding interaction in these electric connections, such as switches. So we would like to be able to quantify the amount of wear of these material.
One of the slides shows the ending with the annealing process. Annealing, what is the purpose of annealing at the end of the experiment?
The annealing purpose was, I showed that when I was talking about the hard disk drive initially. The hard disk drive, this annealing process is different from the annealing process that you use for metals, which is to relieve stress and all that and increase ductility. In this case, the annealing process was done at a certain temperature for a certain time to remove the amount of physically bonded organic molecule. The way we lubricate the hard disk drive is by dip coating. You take your hard disk drive disk and you coat it in the lubricant and you pull it out, and you have a very thin layer of lubricant on the surface. The bottom layer is chemically bonded to the hard disk, but the top layer is sort of attached physically to van der Waals force. So we would like to use annealing to be able to evaporate these physically bonded molecules to create enough number of bonded versus non-bonded lubricant to control the stiction. So annealing was done to remove the physically bonded organic layer.
So it was a very wonderful lecture by Professor Kim. He had touched upon areas like macro scale, micro scale and nanoscale wear phenomena, and the need to study that, the experiments they have conducted, especially using hard disk drive, the studies on the hard disk drive surface, nano wear test using airfoam, silicon, the wear of silicon bushings. One of the interesting topics was the micro ball bearings. Steve has proved that it definitely works, combined with the nano lubrication. The mechanochemical etching on various materials, that could be a substitute for the photo etching or the photolithography technique in MEMS fabrication. The lecture concluded with atomic scale design of surfaces. So nowadays it has become very important. The macro scale, macro level, you have a surface texturing and lubrication. At the nano and micro level, probably the surface needs to be modeled for specific applications. So it was a very enlightening talk, and it described the state of art in micro nano wear studies. As a token of our gratitude, we would like to present a memento to Professor Kim. May I request Professor KBN Nambudipad to come over and hand over this.
It's my pleasure and privilege to hand this over to Professor Kim.
Thank you. Thank you.